Hi, my name is Jong-hyuk Park from Hamgyong University of Foreign Studies. This work was done in collaboration with Seongkyungwan University and Simon Fraser University. Mijin An is also a first co-author. In this talk, I present the MV Seeker boosting OLTP performance with non-volatile DIMMs. By introducing MVDIMM into the DRAM SSD hierarchy as a durable write cache, this can significantly reduce durability overhead. The non-volatile DIMM presents great opportunities to bridge the performance gap between DRAM and SSD. However, due to the high cost of MVDIMMs, using large ones as a single buffer to keep entire pages isn't cost-effective. We focus on the MVDIMM for two main reasons. OLTP workloads typically have small and random updates, which entails a lot of cache flush operations. When compared to Intel Optane DCPMM, MVDIMM provides lower latency and higher bandwidth. This offers optimization opportunities to leverage a compact MVDIMM buffer. And many existing DBMSs already exploit the DRAM SSD two-tier architecture, which involves frequent I/O system calls to ensure durability. By using MVDIMM as a durable buffer, we believe that we can significantly reduce durability overhead. Now, let me explain the primary reason we use MVDIMM as a durable cache and how the compact size of MVDIMM is advantageous. OLTP workloads exhibit two primary write characteristics, temporal locality and write skew. First, specific pages are often written to repeatedly over a short period of time, and certain tables have a small number of tuples periodically updated frequently for a short period. As is widely known, 80% of accesses go to the hardest 20% of pages. As a rule of thumb to determine the access interval for caching the memory, we use 5-minute rule to explore the break-even interval between MVDIMM and SSD. When MVDIMM is used as durable cache for SSD, then we can get the break-even interval as 106 seconds. It means if a page written to SSD every or less than 106 seconds are better to be cached in the MVDIMM. Then, next question is how many pages are active within this time window. As the size of MVDIMM is much smaller than that of SSDs, MVDIMM cannot absorb or write up pages if there are too many within this time window. To determine whether MVDIMM can be used as a cost-effective cache for OLTP workloads, we ran the TPCC benchmark for 6 hours and measured the percentage of pages written at least once every 106 seconds. This figure shows the fraction of pages written more than once within this time window out of the total number of pages accessed in the same time window. We observed that OLTP workloads have a small write working set, approximately 0.54%. So we present the MV Seeker by using the MVDIMM as durable write cache. We can reduce the write traffic to SSD. While the idea of using MVDIMM as a durable cache for hot data is very simple, but realizing it existing relational database engines has few challenges. First, it's important to determine which write-up pages should be cached in MVDIMM. Therefore, we introduced a page admission policy to identify write-up pages when they are evicted from the DRAM buffer pool. To detect the most write-up pages, we use two database semantics, checkpoint and log sequence number. First, we exploit the first checkpoint, which asynchronously flushes 30 pages from the head of the 30-page list. MVC-curl regard checkpointed pages are write-hot pages because they are accessed frequently enough not to be kicked out by earlier replacement. Second, we leverage the LSN to estimate write-hot pages. We define the re-update interval as gap between first update LSN and last flush LSN. First update LSN is the log sequence number when a page is updated for the first time after being fetched into the buffer. Meanwhile, the last flush LSN is the log sequence number when a page is flushed to disk for the last time. This gap indicates how quickly edited pages are brought back to cache. Therefore, pages with a short re-update interval can be considered as write-hot. Next, page action consistency problem. In traditional DRAM SSD architecture, inconsistencies with cached pages are not a concern because DRAM is volatile. However, since we use NVDIMM as durable light cache, partial update to NVDIMM pages become immediately durable. This creates the potential for page action inconsistency in the event of a system crash. To tackle this problem, several approaches have been proposed. The first is the copy-on-write version. This method maintains action-constant pages as shadow pages using additional space in NVDIMM. However, it does suffer from space inefficiency as well as memory copy and cache flush overhead. Next, the undo-based version ensures fair atomicity by utilizing undo logs. While PMDK transaction APIs employ undo logging, they also introduce significant overhead. Furthermore, undo logging requires fine-grained and complex logs for micro-operations within the page. This results in a significant memory fence and cache flush overhead. Finally, MVC-curl uses the redo-based page action consistency method. We employ the inUpdate flag to monitor action inconsistency NVDIMM pages. This flag is set during page modifications and is unset once those modifications are complete. As a result, this flag effectively identifies pages with action inconsistency. To recover these inconsistency NVDIMM pages, we apply read logs using older version of the pages stored in SSD. It is important to note that the number of action inconsistent pages is directly related to the number of CPU cores executing logical updates actions. Consequently, the number of inconsistent NVDIMM pages is few. In addition to write-hot pages, there are small, write-intensive objects that are worth storing in NVDIMM, read-log buffer and double-write buffer. By placing the read-log buffer in NVDIMM, we can avoid the overhead due to log4set commit and the while protocol. In particular, we can cut out the need for synchronous log flushing without compromising atomicity and durability. Furthermore, since undo logs are durable in NVDIMM, we can implement a no-while protocol. This obviates the need to flush logs before evicting pages certified by an uncommitted transaction. Next, double-write buffer. MySQL InnoDB engine depends on journaling to ensure atomic propagation for multiple pages. Unfortunately, this redundant write can hamper performance. By placing a 2 MB size double-write buffer in NVDIMM, we can realize single-write journaling by replacing disk I/O to memory I/O. Moreover, for NVDIMM resident pages, we can bypass redundant write to the double-write buffer. This is another beneficial side effect of MVC-curl. MVC-curl extends ARIS recovery scheme. and we made minimal changes to the existing recovery process of vanilla MySQL engine. During analysis phase, MVC curl additionally examined the in-update flag of all MVDIM pages. In the lead page, MVC curl can bypass action constants MVDIM pages. However, for inconstant pages, it's necessary to apply lead logs from the pages on the SSD. And both MVC curl and vanilla MySQL have the same under process. We prototyped the MVC curl using the MySQL InnoDB engine on top of the server equipped with 16 GB MVDIM and device. For evaluation, we use TPCC benchmark with database size of 15.4 GB and setting the buffer size at 20% of DB size. We based our cost consideration on the premise that 1 GB of MVDIM is equivalent in price to 3 GB of DRAM. As MVC curl has the right traffic per transaction, the flash storage can process more read operations. It means that this translates to boost transaction throughput performance. We also observed that ET cost MVC curl is more performance critical than sacrificing the hit ratio. And for the trade-off between more DRAM and more MVDIM, the more MVDIM case outperforms vanilla, but it's not large enough to offset the reduced hit ratio by far. So we believe that finding optimal MVDIM size is important. In our paper, we mostly used the 8 GB DRAM and 1 GB MVDIM combination. Next, we'll learn the TPCC benchmark by varying the MVDIM to DRAM ratio while maintaining constant cost. As the buffer size increases, the average write per transaction decreases due to a higher write hit ratio. Consequently, the performance gap between the vanilla version and MVC curl narrows. However, this gap widens when the total buffer size is decreased. As a result, MVC curl always outperforms the DRAM-only vanilla version. Also, we identified that MVC curl constantly outperforms vanilla on all SSDs. In most of our experiments, we use MVDIM SSD. For SSD with higher IOs, performance improvement is less than other SSDs because it becomes CPU bound. However, write reduction effects are still valid in this case. Lastly, we measure the amount of time to restore the system. During the analysis phase, MVC curl takes slightly more time because it needs to scan additional lead logs and MVDIM pages to detect action inconstant pages. However, MVC curl significantly reduces the read page time. This is because MVC curl can bypass offline read logs for action constant MVDIM pages. For action inconstant pages, read logs must be reapplied to the corresponding old pages in the SSD. Even though action constant MVDIM pages are few in number, they account for about half of the total read logs. So this effectively cancels out this overhead. In conclusion, we introduced MVC curl, which utilizes a compact MVDIM as an extended buffer cache. Moreover, MVC curl takes advantage of both the DRAM SSD architecture and database semantics, such as checkpoint, LSN, and AD-style logging and recovery techniques. As a result, MVC curl significantly reduces write to SSD, and thus it boosts the transaction performance. Thank you for listening, and please check out our paper and code. In the paper, we discuss more details of evaluation that covers design principles of MVC curl. If you have any questions, please feel free to contact. Thank you.